We'll go through a bunch of miscellaneous topics. This is going to be the last lecture. So these are clarifications of some points that were not very clear, or I felt were not very clear, or about doubts that students have asked me through the semester. Okay. So first I'll just go through this optimal equalizer criteria. You already know this, but this is just a refresher. And then someone asked me about the validity of the PLL linear model. I think it was you. And about PLL lock and capture ranges, especially the capture, we have not discussed it. We'll discuss it to some detail here. And then also, as you realize from simulating the Hawk detector, it has a huge offset, and also different. You guys got different offsets, which sometimes was not consistent with the D flip-flop delay. Okay, so we'll see what the deal is with the whole thing. Okay. So we know that with intersymbol interference, if the channel response has length n, that is the discrete time channel response has a length n, and you have binary data, you have 2 to the n possible values, and the received values are spread between 1 minus summation of absolute values of h and 1 plus that. Okay. And given the received values, you have to essentially receive the data with minimal bit error rate. That is the goal. Now, the optimal way to do this is to basically form a tree. Given some transmitted sequence, you can form a tree, like if the first bit was this and the second bit was this and the third was this, you can see what that leads to. Okay, and that way you can form the combination for, you can form all the 2 to the L, 2 to the M combinations and do this maximum likelihood sequence estimation. This is like Viterbi decoding. Okay. So you basically trace the path of the signal, and n symbols can contribute to the received signal at any given point. And given the received value, you can figure out what path it took. That is you decide the path it took with the highest probability. Okay. So that way you minimize the bit error rate. That's what you should do. But the problem with this is if the channel impulse response is long, the complexity of this procedure is too much. You just cannot do it. Okay. A given value is a result of n different symbols. Okay. So, and you receive at every interval, at every sample, you receive some value. Okay. You receive a sequence of values. You also know that if a particular sequence was transmitted, the probability of receiving a certain value. Okay, you can form the probability density function for that. So now there are 2 to the L such combinations, right? So you find out, like probabilistically, you find out given some received value, which one was the closest to what was transmitted, and the closest one is obviously your estimate of what was transmitted. Okay, that will by definition minimize the bit error rate. But the complexity of this process is too much. That's why we don't do the equalization like this. And as the length of the intersymbol interference taps increases, this grows exponentially. Okay. If you have n intersymbol interference, n symbols contributing to intersymbol interference, then there are 2 to the n possibilities. So that is an exponential dependence on n. Okay. So what we considered was a couple of things. Firstly, if the channel response, this is the discrete time equivalent channel pulse response. Okay, if that is h of z, then it can be, the ISI can be completely eliminated by h inverse of z, because the product is 1. Now the problem is when there may be frequencies where h of z is much smaller than 1. Okay, this is because of nulls in the response and so on. If you have 3 identical, if you have 1, 1 and 1, so 1 plus z inverse square will have many nulls in it. Okay. So if you have a lot of ISI, you could have nulls, and in reality, you could have nulls because of reflections and so on. Okay. So if you try to invert it, clearly you have to provide a large gain where h is very small. So that means that the noise at those frequencies is boosted quite a bit. Now in practice also, for a finite length of h, you need infinite length of h inverse. You truncate it in practice. What it does is, it ends up minimizing, actually there should be an absolute value here, okay, this fk, that's an absolute value. So basically, we saw that this is the spread, like sum of the absolute values, and that's what this type of equalization tries to minimize. It tries to minimize the total spread from 1. Okay. And to determine this equalizer is also quite easy. You first simply find the inverse of the channel, inverse of the discrete time, equivalent discrete time channel, and then truncate it to whatever length you feel is convenient. Okay. So what happens is, because of truncation, the resulting combined response of the channel plus equalizer is not 1 and all zeros, but at the ends it will have some non-zero values. Okay. The problem with this is noise enhancement. Now there is also another way of determining the equalizer coefficients. In this case, you minimize the sum of f square. F is the combined response of the equalizer and the channel. Okay. So whatever is, whatever is other than the cursor, you try to minimize the energy of that. Now what happens in this case is, if there is very little signal transmission at a particular frequency, this doesn't try to invert it. It doesn't try to boost it. Okay. That's why this performs more optimally in presence of noise compared to the zero forcing equalizer. Okay. Now, to do this, to find the optimal coefficients analytically, you can use this formula. I don't know if you guys saw the handout on the derivatives of a vector and so on. It's just, you get this formula where A is for finding it for an FIR filter, A is delayed versions of the input sequence, and B is whatever you want to equalize to. The desired response is all zeros and a single one. Okay. So like this, you can find analytically the coefficients that give you least mean square error. Okay. So if you, so this is the one. So if you look at this, it's quite simple. It's like minimizing some x square. So it's all because now you have vectors and the derivatives are matrices. You have to be careful about the order in which you multiply, and sometimes, like for instance, instead of e square, you have to take something transpose that to find the energy, etc., etc. But the idea is the same thing. Okay. So finally, you get so this G transpose G is like G square. Okay. So I don't know if I can zoom this. Yeah. So this G transpose G is like G square, and if you have G square, the derivative is 2 times G times the derivative of G, right? It's the same thing here. It's just that first of all you have to keep in mind the order, and this derivative is the Jacobian of the vector G. Okay. And from that you can derive the condition. Okay. This is the gradient, and if you set this to 0, you get the condition for minimum norm of G. Any questions on any of this? Now, the thing is not just to be able to find the optimal coefficients analytically given the channel response. Because the channel response changes, you have to do it on the fly. Okay. Maybe you don't know the channel response precisely, and maybe it changes from one device to another device. So when you make a chip for a particular type of channel, you are really making it for a class of channels, including some variations that are possible. Okay. So you have to have adaptation. And it turns out you can make an adaptive zero forcing equalizer also, but from the point of view of equalization, the LMS equalization is better. The filter with which minimizes the mean square energy of the intersymbol interfering elements. That is better than zero forcing, and also for adaptation it turns out to be easy also. Okay. So essentially you use what is known as the steepest descent algorithm. So the coefficients are updated using this. So what you really should be updating is using the gradient of the expectation of E square. That is, the expectation of E square is the mean square error, right? But someone proposed that instead of using the expectation, which is hard to find, you have to find some time average or average over something, you simply use the instantaneous value of the gradient. Okay, that was due to Woodrow. I don't have the full reference here, but you can. You can just put that in Google and get the reference. Okay. So it turns out to work quite well in practice. That's why it's very popular. Okay. So what you do, you have this y is the coefficient multiplied by the input vector. Okay. And the error is I'm again considering only binary case, but it doesn't have to be binary. It can be multi-level signal also. So y minus the sine of y. So basically it turns out to be in this particular case the gradient of y with respect to c is simply g itself. Okay. So you update the coefficient based on the product of the error and the input to the coefficients g. Okay. And I think I forgot a sign in the last one. So you can, for simplicity, you can either take the sign of E or the sign of the gradients or the sign of both of them. So the simplest thing to implement is when you take the sign of both. In this case again, this sign is missing here, but that is the simplest thing. And you also from your simulation saw that it converges to a value that is not exactly the same but fairly close to the full LMS. Right? Yes or no? No? It wasn't close?
No, the sign chain was not as good as
Is it? Okay, we'll resolve this controversy later, maybe in the exam. So, in case of an FIR feed-forward equalizer, the gradients are just the outputs of the delay stages, and you have to make some arrangement to get them. And you also have decision feedback equalization, in which case it's like even more easy to get it. So they are simply delayed version of the decisions. Okay.
So in decision feedback equalization, we are basically taking feedback
Yeah.
around zero.
Yeah.
But that is what we avoided for quite a long time, saying limiter to close the loop and take me.
Yes, that is true to some extent. Yeah. So in fact, the biggest challenge in decision feedback equalization is to close the loop within one cycle. But one of the things is because it's digital, it's a little easier than if you make a full IIR filter. And secondly, it offers so many advantages that you just do it. Okay. Yeah, that's correct. So, I mean, I just, first of all, I think the indexes are all completely screwed up. This is K and this is N. I'll correct that. I just made this yesterday. But, yeah, you don't have to, this doesn't have to be at the data rate. In fact, you never do it at the data rate because, first of all, it's not necessary. It creates too much noise in the coefficients. It varies too much. Okay. As the input signal is also noisy, right? The gradient is noisy and everything. Because of that, there will be too much chatter in the coefficients. And if you try to do it at very high speed, you consume too much power. So from both points of view, you don't update it every cycle. In fact, you update it infrequently, and in many cases you adapt it. Once the coefficient settles to some value, you just turn off adaptation and maybe restart the adaptation later when you need it. Okay. So the decision feedback equalizer works on subtracting the intersymbol interference from the past decisions. Now it can eliminate post-cursor ISI without noise enhancement. That's the biggest advantage. Okay. If you use any kind of linear equalizer, it will enhance noise, whereas this doesn't. So what you end up is with a much lower high frequency boost compared to a linear feed-forward equalizer. Okay. Now there is a possibility of error propagation, but in practice this has been found to work just fine. Okay. The biggest challenge, like I just mentioned, is closing the feedback loop within one cycle. Okay. So because the feedback quantities are digital, it's a little easier than to do it with a feed-forward equalizer. Okay. So this is all about equalizers. To switch to a completely different topic. So there was a question, why is the phase detector really nonlinear? So what we do, so this is the output of a phase frequency detector. This is up minus down. Okay. I am assuming that only up is active, so it is positive. So if you have a phase of delta phi, it gives you 1 for delta phi and then 0 for the remaining period. Okay. So you get a certain average value plus some AC value. Now if you double the delta phi, what you get is not this waveform that is doubled. Okay. you get the width of the waveform is doubled, not the height. So, in a purely linear system, you for 2 times the input, you simply get 2 times the output waveform. So, the average value is doubled, but the AC part has changed to some different waveform, which is not really related to the first one. Okay, that is, I mean, that shows you that it is not really exactly linear. Now, if you write so this phi div is what comes back in the feedback loop, okay, in the PLL. What I have written here is the transfer function between that and the phase error that comes out of the subtraction, phi ref minus phi div. So that's basically the loop gain, okay. So that has some kind of a low pass function, right. So this is the output of the differencing block. This is the output of the phase detector. Now, when it goes through the loop and comes back, it goes through this transfer function. Okay. So it has some kind of a low pass response. Now we know that the DC part of it varies linearly with the phase and the AC part of it doesn't. So if the low pass filter sufficiently cuts off the AC part of the phase detector output, then you can approximately treat it as a linear system, because the output is really non-linear, but the non-linear part is killed by the low pass transfer function. Okay. So what does it mean? So this is the loop gain. So where the loop gain becomes 1 is the bandwidth of the phase lock loop, right? Roughly speaking, that's the 3 dB frequency of the closed loop system. So this means that when the reference frequency is much well beyond the bandwidth of the closed loop system, or well beyond the unity loop gain points, this AC signal is completely killed and you have an approximately linear system. So that's why you say that the linear analysis is valid only when the loop bandwidth is about 1/10 of the reference frequency or even smaller than that. In practice, it's even like much smaller than 1/10, even 1/100th or something, typically. So you just use linear analysis, but it's not exactly valid because of this reason. This is okay?
When it has to lock, this will come into it.
Which will?
But DLL is yet to lock.
Yeah.
This will be in
This will be in? No. So this is even after locking. This is the case, right?
But before locking?
Before locking, it is definitely nonlinear. The capture process is nonlinear.
This can cause something.
No. This is a problem for analysis, right? Not necessarily for the operation of the PLL. Okay. So we don't use linear analysis for analyzing capture. We use it only for lock and then some small changes around the lock. So then it is okay. Yeah. So this is still phase, right? See, first of all, if you change phase by small amount, whenever you change phase, you are also changing frequency implicitly. Okay. So it's just by the rate at which you change it and the amount by which you change it that decides whether linear analysis is still valid or not. Yeah. No, this analysis is valid even in time domain, right? So let's say you apply a phase jump. So based on the closed loop transfer function, you can find out the output phase jump. So you know that that relates the increment in the input phase to the increment in the output phase. You add that to the operating point and you get the right values. There is no issue there. Okay. So only if you jump the input frequency by a large amount, you can't use this. No, it is, yeah. So the linear analysis is approximate. So you can deal with the AC part of this separately by treating it as reference feed through, right? It won't get fed back if the reference frequency is much more than the bandwidth of the loop. Is it okay? Next thing is to do with lock and capture ranges. So lock range is essentially the range over which the PLL can potentially lock given the right initial conditions. Okay. So or let's say you start with the lock PLL, then you slowly increase or decrease the frequency and it will stay locked. You find out the range over which it stays locked. Or you apply like very small steps, it will go and lock to that step, let it lock, then you apply a next step and so on. So it's a quasi-static process. That's what we are concerned with. Now, this is limited by the range of some component in the loop. This is more like the swing limit. Okay. So it can be limited by the range of the phase detector or the range of the VCO or some range of the voltage, whatever. Now the capture range is a dynamic phenomenon. Let's say you start with a lock PLL and then you apply some frequency step, whether it actually locks to the new frequency or not. Okay, it may or may not do that, or it may take an extremely long time to do that. Okay, so it is a very nonlinear process, and that's what capture is all about. And this is important in cases where you have to switch frequencies, especially in radios and so on. If you have frequency division multiplex, or for some reason you have to switch channels in a given period of time. And the best example is in GSM phones. You have, like when you're talking, you're transmitting on a different frequency. When you receive, you're receiving on a different frequency. So you have to switch back and forth between the two. Okay. So for that you do need some switching speed requirements. But there are many other cases also in which you have to be able to capture within a given amount of time. And for that the capture range and the capture time are important parameters.
So the capture range is a frequency, right? The largest frequency step. So it should be like capture frequency and what is the range?
No, it's the range of frequencies over which the capture works.
But we're talking about a specific larger frequency which can be applied for the
Yeah. I mean, here both lock and capture range have dimensions of frequency, right? So when I say lock range, I mean some frequency. So similarly, the capture range has some frequency. Yeah.
Does it mean that if we, within the lock range, if we apply any height step, does it mean?
So let's say you start with it may not. So let's say you have a lock range, you have a PLL that works from 1 gigahertz to 1.1 gigahertz. So it is locked to 1 gigahertz, you apply a 0.1 gigahertz step, it may not lock. It may not relock to the new one. Okay. Whereas if you take it slowly, if you ramp it up slowly, you go from 1 gigahertz plus 1 megahertz plus 2 megahertz and so on, it will go all the way to 1.1 gigahertz. Okay. Yeah, I'll discuss that. No, lock range is definitely greater, right? So if it is outside the lock range, simply means that the PLL cannot operate at that frequency. So the capture range just says that if it can do it within a certain time or if it can do it when a step is applied. Okay. So the lock range is in a type 1 PLL, it may be limited by a phase detector range, but this is not very relevant because you end up building type 2 PLLs anyhow. In a type 2 PLL, the steady state phase error is independent of frequency, so it's not limited by the phase detector range. Okay. So it may be limited by the range of the VCO. Okay. You always have a finite voltage swing. So, or when you make an LC VCO, you have a finite range of capacitance variation. So you can't have unlimited range. You will have only a finite range. And it may be limited by the loop filter output voltage range. Meaning the loop filter, the VCO may be tunable, but the loop filter swing limit will limit the range over which the VCO can tune. Okay. So, and to get rid of this limitation, somehow you have to increase these ranges, that's all. Okay. This is like increasing the swing limit of a circuit. So if your circuit is only swinging 1 and you want 1.5, you have to somehow adjust the circuit or maybe increase the supply or something. Okay. That's the only way to increase the swing limit. So this is like that. This is like the swing limit of the circuit. So capture range. Now, this also depends a little bit on how the phase detector is designed. So if you design a phase frequency detector, if the input and feedback frequencies are different, there is a definite non-zero DC value. Okay. If the input is greater than the input frequency is greater than the feedback frequency, the average value of the PFD output is more than 0, and if it is less, that is less than 0. So now if you pass a positive current through the loop filter, which is an integrating type of loop filter, the loop filter output will go on increasing. Okay. So at some point it is going to capture. Right. So it may take a long time for a large frequency step, but it is going to capture. So essentially in this case the capture range is practically equal to the lock range. The limitation comes from similar limitations as lock range. Okay. This is because the phase frequency detector gives you a definite indication of whether the input frequency is more or less than the feedback frequency. Now you can use other kinds of phase detectors. So in case of a PLL, you may use a multiplier or an XOR gate. XOR gate is nothing but a quantized multiplier, right? Or in case of when you are talking about data recovery, you say Hogg phase detector or Alexander phase detector. So these things give you a non-zero average value only when the input and the feedback frequencies are the same, but there is a phase difference. Okay. If that's not the case, then the average value turns out to be 0. Okay. But the output will contain a difference frequency component. I will show that in a moment. So if what happens, it turns out, let me go to the analysis of so let's imagine a phase lock loop like this. In this case, instead of XOR gate or PFD, I have assumed a multiplier to be a phase detector. Okay. Now I assume that these waveforms are sinusoidal. Okay. Why is it so misaligned? So I assume that these waveforms are sinusoidal. So at the output of the multiplier, I get the sum frequency and the difference frequency. The sum frequency is so high that I assume that it is attenuated by the loop filter. Okay. And I assume that the difference frequency is not attenuated. So let's see what happens. Okay. Now if the input frequency is greater than the feedback frequency, the control voltage must increase. Now what I have drawn here is sinusoidal waveforms of different frequencies. Okay. So let's say the difference frequency is initially the first sinusoid, the highest frequency that you see. So what happens? The control voltage is increasing, right? Now as the control voltage increases, the output frequency also increases. So the feedback frequency increases and the difference frequency falls down. So you can say that the control voltage switches over to the next curve. In reality, it's a continuous process. I am showing it as like stepping from one frequency to the next one and next one. So it will do this, and then next it will switch to the further lower difference frequency, and it will do this. So essentially, if it starts off, if V control starts off increasing, you will end up with a large positive pulse like this. Okay, it keeps getting broader and broader. Is this okay? No. So this corresponds to a high frequency difference. This is a lower frequency difference, lower and further lower. So as you start off like this, it will switch over to lower and lower frequency differences. Yeah. So in this case, there is no divider. So it's just FRF minus FVCO. Okay. With a multiplier, when you feed two frequencies, you will only get like two other frequencies out, right? So you get FRF plus and FRF minus. Assuming the sum frequency is completely filtered out. So it will do this. So essentially what happens is it may lock immediately, or at least it will looks like it is giving you trying to give you a larger positive DC average value, right? The positive component is increasing. So this I assume that the control voltage started off increasing. Let's see what happens if it starts off decreasing. So let's say initially the difference frequency was this curve. Okay. So the control voltage follows that. Now as the control voltage reduces, the difference frequency increases because the VCO is being taken away from the input frequency. So it will switch over to the next one, and that will further increase the difference frequency, and it will switch over to the next and so on. Okay. So what happens is if it starts off in the wrong direction, the pulse tends to become thinner. If it starts off in the right direction, the pulse tends to become fatter. Okay. So on average, it will move towards the right direction. Is it okay? So, is it okay or no? No, wrong. So in this case, I have assumed that the input frequency is more than the feedback frequency. That means that the VCO frequency has to be increased, which means that the control voltage has to be increased. So increasing control voltage is the right direction, decreasing control voltage is the wrong direction. Okay. So because of the feedback action, this tends to thin out and the other one tends to become fatter. Huh? No, it may just happen that, that depends on the phases of the signals, right? So when you multiply two signals, you can start off with the negative part or the positive part of the sinusoid. That you can't help it. That simply depends on the initial condition of the system.
VCO frequency increases.
Yeah.
The control voltage also will try to increase.
Yeah.
Started to increase, but why is it going back?
No. See, the control voltage is the difference frequency component from the phase detector. Okay. So, the control voltage causes the frequency, not the other way around. So, what happens is, when the control voltage reduces, the difference frequency increases. So, I will say that it switches from this curve to this curve. Okay. And next it switches to this and switches to this. So, it is only when the control voltage becomes positive again that it will start increasing. Okay. So, essentially if you look at a PLL under capture, so let us say it starts off like this. So, even if it starts off positive, it may not capture immediately because, so it will follow this, but it may eventually fall off because the time is not sufficient for the frequency of the VCO to have changed to the right value. No, it is moving in the correct direction, but as it reaches the peak of the difference frequency sinusoid, it also moves back in the wrong direction, right? Isn't it?
That case, as we are moving towards smaller and smaller equipment is LPC.
Yeah.
It means that the bus is getting broader and broader. So
Yeah.
it should finally settle to the peak value.
No, no, it may not, right?
Small ripple around that right now.
No, why?
Start dropping again.
No, because the control voltage is the difference frequency component of the, from the phase detector, which is a sinusoidal curve, which goes up and down, that's all. So it does tend to do that. So it can in fact do something like this. Okay, it will do this, but then these things will become progressively thinner, and also their levels will get elevated because of the larger DC value. So the next cycle the error is less, and then it may do something of this sort.
Change is because of the output control voltage is also oscillating. That's also
Yeah, the control voltage is at the difference frequency. In case of a multiplier, it will be a sinusoid. Okay. Yeah, it goes and it can come down and go back up and so on. So because the VCO frequency is exact here, so there it remains constant. So essentially what happens is the average of the V control increases progressively, resulting in a higher average frequency. So this happens if the difference frequency component is not attenuated by the loop filter. Now if it gets significantly attenuated by the loop filter, the amplitude of the correction that you get is very small. So this process may not build up. Okay. And I have something here, let's see. What else is there in this? No, this is different. So I have a slide to show the so this is a actual simulation of a, can you see the curves? There is a, yeah. This is a simulation of a PLL with a multiplier phase detector. Okay. And what the free running frequency is 1 gig and the initial condition is also 1 gig. Okay. Now I apply an input of 1 gig. What happens? It is still not captured. The free running frequency may be 1 gig, but initially there will be some non-zero output from the phase detector, and it will actually move away from 1 gig and come back. That is the red curve here. There is a small deviation, but then it finally settles to 1 gig. Okay. Now I apply 1.01 gig. I think this PLL in fact had a loop bandwidth of about 10 megahertz. Okay. Or 20 megahertz. It's this is near the range of this is within the loop bandwidth. Okay. So you can clearly see the curve that I just described. So it will do this, and it is the top pulse is getting fatter, but the negative part is getting thinner. The second time the top pulse is even fatter than the first one. Okay, and the negative one is thinner. The area under that is lesser. So it is building up, and third time it doesn't come back at all. Right? It just goes and settles to the right value. And I did the same thing with 990 megahertz. It does the opposite. Okay, and also you can see it's nonlinear. When the frequency difference is positive, the curves are not exactly the same, right? It just goes in. It's roughly the same behavior, but the curves are not mirror images of each other. So is this okay? So this is how a PLL captures. Now, this is now I step it from 1 to 1.2 gigahertz. So I've done two things here. Again, it's the same PLL. I have ramped the input frequency. Okay, I have not stepped it. I have ramped it slowly with over 800 nanoseconds. So you can see that it clearly it is essentially maintaining lock throughout and finally settles to this value. That is the red curve. Next, instead I apply a step of 20 megahertz. Okay. So then it is not doing it. Actually, you can see that this is, in this case, everything is ideal. So in fact, if you wait long enough, this will probably go and capture it. But you can see that it is very slowly building up. When I change the frequency slowly, it's able to maintain lock and it actually goes to the final value. But when the input is fast, it's not able to do it. Okay? No, this is again because the difference frequency component is also getting attenuated. I told you that this is 20 megahertz. Right? So I think I didn't apply a large enough difference. So this is a 20 megahertz difference. Okay? The bandwidth of the PLL is 10 megahertz. So the loop filter is attenuating this part and loop filter is attenuating the control voltage. Okay? See, the control voltage is what causes the VCO output to increase. Now if the control voltage tends to go positive, the output increases and the difference reduces. Now, before being applied to the VCO, it is getting attenuated by the loop filter. So, in that case, it's not, there will be a control voltage increase, but not as much. So, that's why it is not able to capture fast. Okay? No, because this is an ideal case. So, what happens is, whatever I described still happens, but much more slowly. Now, the control voltage is small amplitude. So, in every cycle, the positive part is getting fatter and the negative part is getting thinner. Okay? But to a much lesser degree than before, because the amplitude itself is attenuated. So, you can see that phenomena here also. And clearly, in these parts, the waveform is kind of non-sinusoidal. This positive thing is fatter than the negative. Okay? Now, with everything ideal, it may still capture, but it will take a very long time. No, also as you go negative, the difference frequency increases. So the difference, it's even getting thinner. Okay. No, that's true. The only distinction here we are making is if the phase detector will give you a sinusoidal output at the difference frequency. If the difference frequency is also attenuated by, let's say it's attenuated infinitely. Okay. Let's say in fact this is a ridiculous case, but the loop filter has a notch at some frequency and the control voltage is nulled out. Then the input to the VCO is 0, right? So it will simply keep oscillating at the free running frequency and there is no feedback. So what I am saying is if the difference frequency component is attenuated significantly by the loop filter, then essentially it is like breaking the feedback. So it may not build up sufficiently to capture the input signal. So in this case it is going to capture, but it will take a very long time. That may not be acceptable also. Yeah. I think locking range you do know anyway, right? If the VCO oscillates and the loop filter works over that range, it will lock. Yeah. 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 So the question is whether it will capture or not. Yeah, that's what you should simulate and see. Yeah, so, okay, you are saying the frequency step became too much. What is the loop bandwidth? 10 megahertz. Then I have to think about the problem a little more. This is for the data also or the data? Okay. Yeah, I'll think about it. Anything else? So first of all, this is a completely ideal simulation. So let's say if the phase detector had some dead zone or something, it won't respond to very small variations. So in that case, if everything is ideal, even a small, the infinitesimally small voltage will give you some phase variation at the output of the VCO, and that will cause further phase variations in the feedback. If the phase detector has just even the very small dead zone, that won't happen. Okay. In that case, I mean, you won't see this, you will just see this going up and down. The VCO will be at free running frequency and the input will be at some frequency. So the difference will have 0 average and that it will stay there. Okay. But I think you can't really talk about capture range without talking about the time. Of course, there will be some cases where it will completely fail to capture, but if it takes like infinitely long and goes through some random process before capturing, that's not a good thing either. So I have to examine the range in the assignment. I think I just gave it for the PLL, but I mean I was thinking of it for the phase frequency detector, in which case it's not an issue, but in this case I have to see if it works or not. So again, it's not that it will certainly not capture also, because in this case it is going towards capture. Okay, it will just take a long time. Huh? Yeah. Yeah, that's correct. Yeah, it should capture. So this, the same thing happens, a similar thing happens with XOR phase detector or Hawk phase detector. The output of the phase detector will contain a difference frequency component, and that will again go through the same process of building up the positive parts and maybe making the negative parts thinner. So this is just so in this case I have taken a Hawk phase detector, and in this case the 5 cycles of the clock equals 4 cycles of data. Okay, so the clock is faster than data. So if you look at the up and down pulses, the down pulses will always be half a clock cycle wide, right, in case of a Hawk detector. And there is a missing pulse here because you see that this rising edge and this rising edge are sampling the same data value. So there is no transition. As far as the samples at the clock edge are concerned, there is no transition. So similarly, the up pulse doesn't have anything here. It has something here, here and here. Okay. And this whole thing repeats after this period. Okay. Now if you look at the average value of this minus this, it will be 0. But you can see that this has a periodicity at the difference frequency. Okay. So a similar thing happens in case of data also. This is okay. This is just to show that the up minus down will be periodic at the difference frequency. Okay, and I have taken 5 and 4, but you can take n and n plus 1, it's easy to see. In any other case also you can see that. So this is again a simulation. Now what I have done is, I have low pass filter, so this is just a phase detector, there is no loop. Okay, the phase detector is operating with some frequency data and some other frequency clock. So in this particular case, the clock is slower than data, it's 19 by 20 times clock is faster than data. Okay, and clock period is 1 nanosecond. So I have taken up minus down, that gives you something like this. You can see the pulse width is larger in these parts and smaller in these parts, and then it repeats in this. Okay. And I have low pass filtered it simply to remove the high frequency components. So it will give me some periodic signal like this. Okay. And the average value of that is, this is not the Hawk phase detector, this is the phase frequency detector. So the average value of that is definitely positive in case of a PFD. Okay. Now I increase the frequency difference. Before it was 19 by 20, now it is 9 by 10. Okay. Now the average you can see that the frequency of the output has increased. Okay. And the average value has reduced a little bit. Yeah, so what I have done is to take the phase detector output up minus down and pass it through a high order Butterworth filter. Now in this case, I think the second harmonic of this was also passing through the Butterworth filter. In the next case, it's only the fundamental that's passing through the Butterworth filter. That's why. So for a Hog, so in this case you saw that the waveform is always positive, right? When the frequency difference is positive. Whereas for the Hog phase detector, the average is about 0. The purple line shows the average over some period. So it's not exactly 0, but it's close to 0. Okay, but there is a difference frequency component. So this is similar to the multiplier case that we discussed. The average output is 0, but there is a difference frequency component. So in this case, what will happen is if you put this in a loop, the positive parts will tend to get fatter and the negative parts will tend to get thinner, and then it will capture, hopefully. Okay. Now, what I do is, this is for a certain difference between data and clock frequency. I increase that difference. That is, I take the data farther away from the clock frequency. So, what you see, the average is still 0, but the amplitude of these variations is reduced. So, it will definitely take a longer time to capture if it does it at all. Okay. Minus, see, that is, actually there are some transients and so on, and I have taken the average over some part.
But in the mark frequency, the average of here, basically sampling at just in the middle of the clock, and the base is completely matched.
Yeah.
We should have a 0 phase difference.
No, this is, we are talking about Hawk phase detector with different frequencies. So, you can't say that it will be in the middle. It may be in the middle for one cycle, next cycle it will be different and different and so on. Okay. So, in this case also the average is 0, but the amplitude also has reduced. So, the build up process will take longer, the capture will take longer as the difference frequency increases, and if this amplitude becomes very small, it may not capture at all. Okay. So, the same thing happens with bang phase detector. Okay, the bang phase detector, again it has the difference frequency component, and when I increase the difference frequency, there is still a difference frequency component, but its amplitude has reduced. The scales are all the same in all cases. So, is this somewhat clear? The capture is a nonlinear process, and if you attenuate the difference frequency component significantly, the capture process will become very slow or may not capture in some cases. Okay. So, in practice what is done is, when you have a clock and data recovery circuit, you have a frequency acquisition aid to this, because the range over which it can capture is quite small as a fraction of the data frequency. Okay. So, to speed up capture and to help in capturing, you have a frequency acquisition aid. I will show an example in a moment. I don't know if this is the last one. Yeah. For phase frequency detector, it will, that itself is the acquisition aid, right? It will tell you which way the frequency is. But if you have just this phase detector, it won't. So, you have to add something to it to do it. So, I will just show you one quick example of what we had done in one of the transceivers. So, this you can refer to other aspects of this paper, but I will show just the. So, this is exactly what we discussed in class. This is the system that's implemented. There's a feed-forward equalizer, but this is a continuous time analog filter in this case, and a variable gain amplifier and a DFE, okay, and a clock and data recovery. This. So, this is a bang CDR. The top part of the circuit shows you that it's in slightly thicker lines, I think. But to let it lock, and it also has to work over a reasonable range of frequencies. So, what happens is the VCO has multiple capacitors. You can switch in and out capacitors. It's like band tuning on the radio, right? It tunes to different bands. With a single capacitor, you cannot vary the frequency continuously over a wide range. That's why we do this. So, there are in fact two acquisition aids. So, firstly what happens is the reference frequency and the divided frequency is fed to a frequency comparator. This is a counter. You count for a given number of pulses, see the difference in counts from this and that will give you an idea of the difference frequency, right. So, you are just counting the number of cycles in a given time, and based on that you switch the correct range, and after that it becomes a PLL with a phase frequency detector. So, this loop is complete. Okay. So, it becomes a PLL and it captures it. So, see, this is coming from the other chip which has a slightly different reference frequency from this one. But this will capture to, the PLL will lock to this reference frequency, and after that you switch over to the CDR mode. Okay. So, it's you have these things in practice in general, and it may be in different forms, but in general there should be some measure of frequency difference that also is taken into account while setting the control voltage. That's the basic idea. Okay. See, first of all, when we discuss phase detectors, we said that we will essentially look at the information only at data edges. So that kind of philosophically means that if you have harmonics and so on, it can do it, right? Yeah. No, it should not happen. As far as I know, I mean. I don't know if there are other unstable equilibrium points which in simulation are stable. We'll look at it afterwards. Okay. Yeah. So this is a transceiver. So there is on each side there is a reference frequency. So this is a transceiver chip. So for the transmitter you need the reference frequency anyway, right? So that is available for the receiver also. So I don't want to spend too much time on this, but this is the chip. It has 4 transmitters and 4 receivers. Okay. That's true. Actually, in many cases you see papers that are titled reference-less frequency acquisition. So that is somewhat of a big deal. But in many cases, when the reference is available, it is wise to just use it. But if it's not available, reference-less frequency acquisition is also a big thing. Okay. No, I mean, receiver also, if you are willing to make a provision for a frequency reference, you can do it, right? See, I mean, generally even a digital chip needs some frequency reference. It may not be very accurate or its accuracy requirements may be different. So if that's available, you just use it. So it's all these decisions are based on the system and the system cost, etc. Huh? Yeah. No, that is, that is like the most basic thing you do. On a digital chip, you have the data and the clock together. But when you first of all are sending data over long distances, this may not be feasible. You don't want to spend another thing for another line for just the clock, especially with things like Ethernet, etc., etc. So we are talking about cases when the clock is not sent. Basically, it's not a synchronous communication. That's when you need this serializer, deserializer, and the clock recovery combination. Okay. In fact, clock recovery is more fundamental than equalization. You may not need equalization if the channel is good enough, but you will need clock recovery. Okay. So I think we are out of time, so I'll just quickly go through the very last thing here. So the last thing was not, see the Hawk phase detector, we say that it has a problem with the clock to Q delay because the up pulses are wider than they are supposed to be. So you can compensate it by putting a delay in front of the XOR, right? Now the additional problem is that the XOR also has a problem, it is asymmetric. The delay through one of the inputs is different from the other input. So you can use it here, okay? So if you make this the slow path and this the fast path, it gives you some effect like this. Now of course in reality both XORs have this asymmetry. So what you need to do is, I think something like this. So you put the slow input in this side and slow input on that side. And if the delay of the XOR gate happens to be half the clock to Q delay, it will exactly compensate. Okay. So this is the reason why many of you have got some clock to Q delay, but the offset doesn't really correspond to the clock to Q delay. So if you put the delay on this side, it will make it better. If you put the delay on this side, it will make it worse. Okay. So that's all I had to say. So anyway, it was actually quite fun teaching this class. I think this is the most responsive class I had in the 5 semesters that I've taught here. So I hope you had fun also. If you didn't, I think Prashant has the evaluation forms.